next panel that will start now, but because we are running a little bit late, we'll catch up, hopefully. So the next panel is called Living on the Moon. And so we have Dr. David Livingston as the moderator for this panel, and three our distinguished speakers, panelists, Dr. Bhavya Lal, Dr. Ajay Kothari, and Dr. Haim Benaroya, representing entrepreneurs, private companies, NASA, and universities. So let me introduce Dr. David Livingston. When I read his bio, I tell you, every time I read his bio, I just get so intrigued. So Dr. David Livingston is the founder and host of The Space Show. If you go to www.thespaceshow.com, a live broadcast, internet radio, space educational talk show program. In the more than 20-year history of the program, with almost 4,000 live radio interviews, The Space Show is the nation's only live broadcast talk radio program focused exclusively on space commerce, space tourism, exploration, science, economics, development, and enabling our growing spacefaring economy and society. Dr. Livingston is also the executive director of the One Giant Leap Foundation that controls the space show and promotes space education. Dr. Livingston has a BA in political science, an MBA specializing in international business management and economics, and a doctorate in business administration from Golden Gate University in San Francisco. His 2001 dissertation was titled Outer Space Commerce, Its History and Prospects. Dr. Livingston is a frequent speaker at space conferences and has published more than 50 papers, including chapters in books and peer-reviewed works. He authored the Space Tourism chapter in Space Encyclopedia and co-authored 3 business and financial chapters in the new Space Mission Analysis and Design textbook called Space Mission Engineering, the New SMAD. Please welcome Dr. David Livingston.
Thank you very much for that introduction, and it is an honor to be here today and to be able to participate with all of you and the people on this panel. This is about living on the moon. So there are some challenges to living on the moon. And I think the first challenge is, how soon can we begin to start living on the moon? I think it's near term, but because it's government led, there's a lot of policy and other issues that may come up. But there's also technologies needed that are not yet in place. So spacesuits are a challenge to deal with the environment of the moon, especially lunar regolith, which is toxic to both humans and equipment. The 1/6 gravity is an unknown for long duration habitats or residents on the moon, radiation. So there are challenges. There are also transportation to and from the moon. If you really want to have living on the moon, you need routine, scheduled transportation. So that does not yet exist, as well as infrastructure, which would be in the cislunar range infrastructure between Earth and the moon. So there are a lot of challenges, and there are people working on these challenges all the time. And we're fortunate to have several of them on this panel that can talk to you about the challenges and how they see evolving to living on the moon. And living on the moon probably evolves to using the word space settlement, meaning maybe it's not just a scientific outpost, but maybe people are living there to create a town or a village or a city on the moon for commercial reasons, for personal reasons, for tourism. But you got to get there first, and you've got to be able to deal with the challenges, and you have to be able to live there safely. And I'm hoping you will be able to go routinely and come back to Earth routinely. So I want to read the bios, but I'm going to do something a little different. I'm just going to tell you a little bit about each of the guests on this panel. Their bios are posted on the conference website. I urge you to check them at your leisure and to read about all of these people. They're very impressive, but if I read them, it'll eat into a lot of presentation time and question time. And I would like to have as much time for the presentations and questions as possible. And I will go in order that the guests appear on the agenda. But first, we are very honored to have Dr. Bhavya Lal with us, and she is serving as the Associate Administrator for NASA's Office of Technology, Policy, and Strategy. Previously, she was a Senior Analyst for Budget and Finance to the NASA Administrator at NASA. In the first 100 days of this administration, she was the Acting Chief of Staff at NASA. In addition, before that, she was involved with the IDA, and she led strategy, technology, assessment, and policy studies, and analyst there. This is the IDA Science and Technology Policy Institute. Again, I urge you to read her full bio, where you can learn all about her. In addition, I want to tell you a little bit about Dr. Kothari. Now, you've already been introduced to Dr. Kothari with a very high quality introduction. So to save time, I would like to say that since I met AJ 3 or 4 years ago, he's been a significant guest on the space show, presenting phenomenal lunar development and economic ideas. I mean, really phenomenal ideas and programs. He's a big hit with guests all over the world. And lately he's been talking about thorium, which he calls King Thorium. Not sure he'll get into thorium today or not, but you've already heard about AJ. Again, go back and read his resume. He's very impressive. He's a great radio guest. So if you're out there with a radio show and you're looking for a great guest, AJ is terrific. So this brings me to Dr. Benaroya, who I met before I started the space show. We were talking and speaking together at engineering conferences in Albuquerque, New Mexico. I'm not an engineer, but I needed to learn engineering to write my doctoral dissertation. So I went to a lot of engineering conferences, and I threw myself on the mercy of speakers and people there to please, please, please teach me, minus the math, a little bit about aerospace engineering. And Chaim and I became very, very close friends. So he is at Rutgers University. He's a professor of mechanical and aerospace engineering there. He has focused on how to build habitats and do lunar construction on the moon. He's written books about it. He's been on the space show for nearly the 20-year history. I'll bet he could take all of his guest appearances and write a phenomenal book about lunar engineering and construction. He also appears a lot with me, with John Batchelor, which is CBS Eye on the World, about lunar engineering and lunar construction. Again, go read his bio, but we want to talk to our guests and hear what they have to say. You don't need to hear me reading about them. So Dr. Lal, what a pleasure to finally get to work with you. And I'm still hoping someday for you to be a great guest on the space show. I look forward to that. Go ahead with your presentation, please.
Thank you so much, David. It's great to see you again. And AJ, thanks again for the invitation. AJ and I go way back. He's a friend of my former boss, Mark Lewis, and Professor Benaroya. So great to meet you, and I look forward to being able to work with you again. So yeah, so you have my slide. I want to share my screen. Can you see my screen?
Yes, I can.
Outstanding. So thank you so much. Yeah, so I just want to say a few things to get started, and then hopefully we will have a really good discussion. At NASA, where I work right now, we are looking forward to a very exciting 2022. This spring, we plan to launch Artemis 1, the first integrated flight of NASA's SLS rocket and Orion spacecraft. Although we won't have crew aboard this flight, we will be sending a suite of science and technology payloads, And we'll get all the data we need to verify the system performance and safety before sending the first crew on a trip around the moon on Artemis 2, 23 or 24, and Artemis 3 would be our first crew landing mission. We'll also begin sending a host of S&T, science and technology payloads to the lunar surface this year under what we call the Commercial Lunar Payload Services Initiative, or CLPS. 2 different companies will deliver instruments on 3 landers, and we have a pool of 14 companies eligible to bid on landing services through CLPS, and I hope we have a chance to discuss this very innovative program at NASA. So let me move to slide 1. Yes, it worked. I was worried. So this is a visualization of our plans to build up our lunar presence. We called it the Artemis base camp, and the names evolve. And this happens sometime after our first landing mission, Artemis 3. So if you first focus on the activities up top in orbit, you'll see that we are assembling a moon space station called the Gateway in what is called a near rectilinear halo orbit. Starting with the Gateway on the far left, you see it nearly complete here, and astronauts will travel and dock to the Gateway in their Orion spacecraft before boarding a lander to the surface. As we progress to the right, Gateway will be enhanced with more capabilities provided by international partners and will include commercial cargo deliveries to outfit the ship and deliver supplies for expeditions to the surface. Now, let's shift to all the activities you see on the surface. At the far left, you see a small lander and multiple versions of it throughout the graphic. These represent the CLPS landers that will be continuing to develop payloads to the moon throughout Artemis. And as I mentioned, by this time, we will have completed our first human landing mission. That first surface expedition will be on foot, but as soon as possible after Artemis 3, we will send the Lunar Terrain Vehicle, the LTV, to the South Pole. This unpressurized rover will provide critical mobility for astronauts to drive while wearing their suits. If you remember, Apollo astronauts were on foot for 11, 12, and 14 missions. When the LRV, the Lunar Roving Vehicles, were sent for Apollo 15, 16, and 17, astronauts were able to travel more than triple the distance from their landers and more than double the weights of samples they collected and returned to Earth. So this early mobility is key to maximizing scientific returns. Next, you'll see a lander labeled Crew Landing Services. This marks the beginning of a services phase for human landers. Much like we are doing now with the International Space Station, we plan to procure landings as commercial services, and this is a huge switch from how we did Apollo. We expect to issue an RFP for landing services. We call it the Lunar Exploration Transportation Services, or LETS, later this year. I can keep going. I guess another thing to point as you continue to the right, you'll see the fission surface power and a pilot plan for in situ resource utilization. And I heard one of the panelists in the previous panel talk about ISRU. The fission surface power, and I'm a nuclear engineer by training, so I'm super excited about that, will support the Artemis base camp throughout eclipses, the lunar light, the lunar night periods when the camp needs an additional source of power. NASA, jointly with the Department of Energy, recently issued a call to the American industry for fission power systems that could be ready to launch to the moon within a decade. So I guess we can talk a bit more about this. Just wanted to give you a quick sense as to the various different things. Want to spend just a couple minutes on the next slide, which is make the point that we are excited about going to the moon, but Mars is the horizon goal, and it is a very important part of our strategy at the moon, around the moon, to prepare for the first few missions to Mars. In orbit, we will be autonomously assembling a ship in deep space and spending years monitoring human health and performance in a true deep space environment. There's also the potential for Artemis systems to be replicated with minor tweaks for Mars. The pressurized rover, for example, could serve as a crew's habitat and rover for a short stay on Mars. I wanna give it, move on to our next panelist. I guess the text you see here in the middle says it all. There's no turning back once crew is on their way to Mars. The moon is a rich scientific destination and a bold ambition for humanity. But while we are there, relatively close to home, let's practice from Mars as much as we possibly can.
Thank you. Dr. Kathari, you're next, please. We can't hear you.
Oh, I'm sorry. Yeah. Thank you, Bhavya. It was wonderful. Wonderful to see NASA's plans, and of course you have seen that before, but it was still wonderful to see that. David, thank you for introducing me. What I wanted to talk about was a couple of things, two things, I guess, in this case. I'm sort of respectfully suggesting, no, let's go back to the previous slide. Just 1 second. Previous slide, please. Okay, yeah, the new paradigm for going to moon and to live there. So I am going to talk about multiple exit ramps to solar system destinations. We can do that for all over the solar system, almost all over the solar systems. And I also want to talk about the thorium-based nuclear power for sustainability. And that is going to be about sustainability on Earth, which is also what NASA is interested in terms of climate change. And also, obviously, source of very much needed power on Moon and Mars, both in this case. So now let us go to the next slide, please. All right, so now what I want to respectfully, but interestingly speaking, say is that the intent here is to propose that we change the way, or I should not say change the way, but we add the way to go to other planets or satellites in solar system, and possibly GEO, starting with Moon and Mars. That we attempt to increase the propellant fraction of the orbiting stage by conducting multiple flights, whether through docking or refueling or combination thereof. So if a flight takes off, it could be SpaceX, it could be Blue Origin, it could be Rocket Lab, any one of those, puts a payload, the upper stage with payload in orbit. And then the second flight within a day or the next day or even the same day takes off. But now it doesn't have a payload in the upper stage. Instead, it has that much more propellant. And those two things dock. And we do that multiple times, maybe 2-3 times. Oh, go back to the previous slide, please. Yes. So what I'm saying is that this is one way of doing something which we can do sort of soon, that we do not try to devise larger and larger rocket solutions for each problem that we may have, that we adopt this as also as a way of doing business, modus operandi, for some cases, most cases, though not all by any means. And this partly is because we have a little bit of an emergency here also, due to confirmation of large quantities of water ice, which I think is like diamonds, as far as I'm concerned, on the moon. So much water ice on the lunar poles, and some adversarial stance of some countries. This need has become sort of urgent. So now we go to the next slide, please. Yes, so this is just an example. Now this example, these are some calculations that were done here. Now so I took the SpaceX's Falcon Heavy, which has flown a couple of times. And if we were to do this, and the upper stage now is a different upper stage, not the Falcon Heavy's upper stage, but a Raptor upper stage. And if we were to do this and put that upper stage with a payload, which is empty of fuel now, how many flights would be required So my calculation showed that 4 flights of Falcon Heavy, and they are, quite cheap now, $50 million, $60 million. A flight is what, has been Elon Musk has mentioned. With 4 flights and all 4 of them docking. So there's no refueling required in LEO. All of them docking, we can take 35 tons and put that on the lunar surface. Now, this is for basically not for people carrying, which would be done by SLS or some other way, Starship, if when it works. But this can be done now because it's available. It's worked. It's been proven. Except the upper stage still needs to be done. So 4 stages docked together can take 35 tons to the lunar surface. The propellant fraction in that case that I need, since it's a methane upper stage, methane LOX upper stage, is 0.779. And I can do that with this 4. If I was to refuel 2 of them, which is the right-hand side of this area, where you can see here the picture and also the table, where 4 of them together will be able to give you, you'll be able to take 41 ton of payload to orbit, to the lunar surface. So what this does is that reusable boosters that we have now, we have multiple permutations available with 3 degrees of freedom: payload size, number of flights, and number mated in orbit. So this allows us to reach different possible solutions depending on the need and the cost that we may be able to bear. So Falcon Heavy as a booster, methane LOX upper stage is used here. So these are a multiple permutation. What this does is it builds a railroad for a solar system by NASA and by all the commercial entities combined together. But NASA should still be in the driver's seat, I think. And this is something that can be done and be available as an option, should be available as an option to us, to NASA, if possible. Okay, so that's one idea. The next slide, please, now. So here is the other one. Now, NASA has shown interest in both terrestrial and off-planet use of this. So what is the terrestrial use? For humanity of Earth, this solution is available today, and I'll talk about the solution in a second. With enough supply of thorium, we have so much supply of thorium in this world that just the amount of thorium that we have in this country will create 700 gigawatt power plants, and that is enough. We have 600,000 tons of thorium in this country itself. So that can provide us enough power to last us 600 years. If you take the thorium all over the world, we have enough thorium to last us thousands of years. So we do not, I think that this is my opinion, that I don't think we need to build space-based solar power stations in geo, etc. This solution needs to be developed right here in America. The time is now for us, for the rest of the pollution-ridden countries, which also need this very badly. No CO2 and energy deficiency problem resolved. Countries to be aware of this technological marvel. One hopes this administration will pay attention to it and find a reasonable path for all of us soon. And this same tech can be used on Moon and Mars without turbines for thermal power and with closed loop turbines for electricity. And so here on the right-hand side bottom is the picture of how it works. And on the top is at the atomic level. What happens here is that the thorium atom, which is at the bottom, is bombarded with one neutron, and then it becomes, it's absorbed, it becomes thorium-233, it beta decays, and it becomes protactinium, and in 22 minutes, very fast. And then over 27 days, it beta decays again and becomes a fissionable uranium-233. And when it fissions, it creates energy which is 3 million times more than the same amount of coal would provide. 3 million times more energy. It's absolutely amazing. And the one below is how it would work. This is molten salt reactor. So the molten salt is, thorium is dissolved in molten salt, and it becomes, it reacts in the way that I mentioned here, and creates heats the water and creates steam, and then runs that power and runs that. We need to do this. This is not being done in this country yet. We need to do this as a very experimental level. We can build with the 3D printing. We can build this, 50 centimeter by 50 centimeter plant, and see how universities can do that, and see how well it can work. So I think that this is really a thing that we should take advantage of as a country, and also for off-planet use. So let's go to the next slide, the last slide, please. So now the this thorium has been detected on the moon also. What does this do? And David talked about, large colonies or settlements. I'm thinking of 1,000 people living there, also the same way that David mentioned. Someday, those people are going to require plenty of energy. They're going to require plenty of electricity and, of course, heat energy. And we have thorium there. 1 kilogram of thorium, 1 kilogram of thorium taken from Earth to the moon. And we know that, that costs almost $1,600 a kilogram now. But it taken there can give you 2.6 megawatt power plant. And that can be really extremely useful. 10 kilograms situated, 10 such plants situated all over the moon or different places on the moon, wherever we, try to settle with those previous thing that I mentioned, where you can, cheaply send a lot of infrastructure from place to place in different places. There, at some point in time, we will have to build larger plants. We will start with smaller plants, of course, obviously smaller electricity generating plant, energy generating plant. But then later on, this is possible to scale this. It's possible to scale the previous thing that I was mentioning about the rocket. And the same way, this is possible to scale this also. So imagine 10 such plants in 10 different locations with 10 kilogram of thorium taken from Earth and associated salt, which would actually weigh more, which will become self-sustaining with lunar thorium. Only the first such plant will require neutron-producing radioactive materials to commence the chain reaction. The U-233 thus produced can provide any further neutrons for additional reactors, thus becoming self-sustaining. For power on lunar surface, however, this is only one of the promising options. Different location may find different solution, such as beam power from SBSP or a combination thereof, as whatever would be ideal for that locale. So these are the two ideas, and I think that as far as our next generation is concerned, new student generation is concerned, it is a very exciting time. Space is beckoning you, it's calling you, but there is a lot to be done, a lot of very exciting thing to be done, very novel thing to be done. And I think it's a great thing it's a great time for us at this point in time. Thank you very much.
Dr. Benaroya?
Yes. It's a pleasure to be here. I want to thank Dr. Kothari for inviting me and David for including me in this panel. And it's a pleasure to meet Dr. Lai. Hopefully we'll have other opportunities to work together in the future. So I want to give a thumbnail introduction to our audience, many of which are not expert in this area, about lunar habitats and just some of the issues that engineers and others have to deal with. Next slide. So I thought it would be fun to see that this is about the 500th anniversary of our first close-up view of the moon. On the left, you can see a couple of sketches that Leonardo da Vinci drew using one of his first telescopes. You can see they're very small sketches, and they show the terrain a little bit. And we've come a long way, of course, in 500 years. But we've been worrying about the moon and what it was and what it was made of, and more recently how to get there and how to actually build a civilization there. On the right, you see a comparison of the sizes. These are radii of the Earth, the Moon, Mars, and the two Martian moons, which you really can't see in this image because they're so small. But I think a lot of people don't realize how small the moon is by comparison to the Earth, and that also Mars is relatively small when compared to the Earth. You can see it's roughly about half the diameter of the Earth, which affects a lot of the issues, and the moon even more so affects some of the issues, in particular the gravity. And what I'll show you in the next few slides are just different concepts for lunar habitats, how they've evolved over the past roughly 6-7 decades. And you'll see some of the early ones and currently are rigid cylinders, prefabricated cylinders that we would manufacture on Earth and bring to the moon. And then they evolve into more hybrid kinds of structures and deployable structures that are inflated and made rigid. And more, no, keep it back there, please. Last slide. And then we have the in situ resource utilization kinds of structures now that that technology has been evolved with 3D manufacturing, layered manufacturing. And given the recent discovery in the past decade or so of the existence of lava tubes under the surface of the moon, people have started thinking about perhaps those locations could be prime for habitats because of the environment. Okay, next slide. So you can see going from top left, concepts from Project Horizon, which were US Army concepts for underground structures. These are pressurized cylinders. You can see they're bearing them. On the right, you can see a Boeing concept for, again, a pressurized cylinder landing on the surface, eventually covered with regolith for protection. That concept was for about 6 people for a 6-month stay. And bottom left and right, you can see inflatable structures, very large structures. You can see the cutaway on the left, 6 levels for astronauts. I don't know if you can see it, but at the very top, you can see astronauts jogging. And because of the 1/6 gravity on the lunar surface, they have to jog almost horizontal to the surface. Otherwise, they can't keep the circle. So these concepts are, futuristic really by today's standards, but they're not as futuristic as they were just even a decade ago. Okay, next slide. So at Rutgers and in the last about 20 years, we've been looking at different concepts for habitats as well as other issues. The one on the left is sort of a pressurized igloo type structure with an artist concept at the bottom left of what an early concept habitat might look like. You can see that it's covered in regolith for shielding. The lunar environment is very dangerous. Well, it has the 1/6 gravity, which affects a lot of the human physiology. We have to internally pressurize our structures. We have to protect them from radiation and micrometeorites, insulate them against temperature extremes. Concepts show 2 to 3 meters of regolith on top. Regolith is the soil on the surface of the moon. Placing it on top provides great protection. The other side of the coin with regolith is it's extremely toxic and dangerous for machinery. So robotics, all kinds of surface operations are severely hampered because of the regolith. And there's a lot of research being done by NASA and elsewhere on how to deal with that. And there is a small seismicity effect on the lunar surface, not really a problem for habitats, more a problem for very flexible structures like antennas and telescopes. On the bottom right, I just list very quickly for you to look over some of the medical and psychological risks. We have cardiovascular effects, bodily fluids shift, vestibular sense is lost, loss of blood volume, cataracts, muscle atrophies, a whole list of things. The bottom one is the pharmacological issues, which I think is interesting because in the low gravity of the moon, our blood doesn't circulate the same way as it does on Earth. And so medicines that we take, like pills and other kinds of medicines, don't work as well, if at all, because they don't circulate the way they do here on Earth. So medicine has to change tremendously for humans to survive on the lunar surface. And also the 1/6 gravity is something that is still an unanswered question as to how the human body will adjust to that 1/6 gravity. We're not even sure how it adjusts to anything other than 1G. And we know that from our space station experiments. So these bring up a lot of issues for long-term human habitation. Next slide. So this is a deployable, inflatable structure that we designed here at Rutgers. If you could play on the top right, it's a short video. It shows the deployment of this structure, at least at the first stage. So the concept is that this structure would be put into a small mode in a lander. The lander would land and it would use its kinetic energy to deploy what you see on the top right. And then from the column, an inflatable structure would deploy, showing what you see there fully deployed. So this is something that we're still building on and trying to develop some of the concepts. But there are many such concepts out there. Next slide. And this is my last slide. On the left, I'm just showing you an image of a lava tube. And what you see there is almost 100 meters in diameter. These are huge, huge caverns that if you can build within them, you can basically protect the inhabitants from almost all the environmental problems on the moon, other than the low gravity. And on the right, you can see a concept for using in situ resources to create a layered manufacturing structure, layered manufactured structures, hopefully robotic, as this image shows. But we shouldn't minimize the challenges of working in the regolith environment on the lunar surface. And I would certainly urge all of you younger people out there who haven't really gotten into college or into their careers too much, that there's a place for everybody in this exploration and the attempt to prepare humans for being a spacefaring civilization. Not only engineers, but all the medical sciences, the business arts, psychology, sociology, all these aspects are important and are needed in this adventure. And I envy those of you who are starting your career, because you'll probably see a lot of great things, from habitats on the moon and Mars and space elevators and all kinds of great things. So it's been a pleasure to be with you all here. Thank you, David.
Thank you very much. Thank you. We do have time for some questions, and I'd like to take the prerogative of the moderator to ask each of you a simple question. It should get a simple, short answer. So, Chaim, I'll start with you since we're the most recent. Can you give us an assessment, an honest assessment of our TRL, our technology readiness level for both putting equipment and working on the moon in the lunar environment, including lunar regolith, plus the TRL for human safety being on the moon? Do we have better spacesuits than we had with Apollo? Give us that assessment, please.
Yeah, I would say that if we're talking about short duration stays, 3 to 6 months, I think we're in pretty good shape. I think that there are serious challenges to being on the moon by human surviving on the moon for the reasons I just mentioned. I think that those challenges are being addressed, but I think that anything that is beyond 3 to 6 months currently is extremely challenging, and there are unanswered questions. We see that with the astronauts that we have in the space station. Even though that's microgravity rather than 1/6 gravity, the effects are going to be very similar on the moon. As far as technology, I don't see really, even though we like to think of robots going there and building habitats, we're not there yet, both from the energy point of view, but again, from the regolith perspective and the radiation environment for the electronics, there are a lot of issues going there. But I don't think it's an impossible thing. I think, we're on track in the next decade to have people on the moon to visit. And probably within a decade after that, maybe a little bit longer, I think we could have semi-permanent or permanent habitats on the moon.
For Bhavya, who gets to visit and carry out research on the Gateway and the Artemis base camp, and what's the process for getting involved in that and getting permission to do that?
Thanks, great question, David. But can I just quickly respond to something Professor Benaroya said? So you said, 3 to 6 months may not be an issue on the moon. I just wonder aloud about that. The longest we were in deep space, the only time we've been in deep space as a human species is the Apollo program, and the longest Apollo missions, and there may be folks in the audience who know more than that, were about 2 weeks. So we have no idea how the human body would react to deep space radiation, galactic cosmic radiations for more than 2 weeks, because that's all the data we have. I mean, this could be a lot of modeling and all of that, but I don't think we can extrapolate from the space station, which is, we've had humans live on a station for a year and longer, but it's a totally different radiation environment. So I think we need to be collecting more data. And again, we may need to send astronauts before we have the data, but I don't know if we can be sure that we can do it. But this is what, again, coming from NASA, this is what NASA is about. We take risks. We are excited to help figure that out. Okay, now on to David's question about the Gateway. So I think one major difference between Apollo and Artemis is Apollo was to be bold, flags and footprints program, right? We landed, we showed we can land, we can do something so difficult with such little technology, and then we were done. Artemis is very different. Here we are trying to really make it a stepping stone to getting into the rest of the solar system. So forget Mars. We are looking really long term at NASA. So what we are trying to develop is sustainable architectures. And again, I think as AJ had mentioned, they can be more sustainable, and we should be thinking about that. We should be bringing commercial entities more. With Gateway, Gateway gives us the opportunity to have multiple ways of doing science on the moon, multiple ways of getting humans landing on the moon. So instead of the direct landing, which we did in Apollo, we could have Orion, our spacecraft, dock to the space station, to the Gateway, and then land. But all of that architecture really, again, and that's another really big difference between Apollo and Artemis, is we go with others. We go with our partners in industry, in the international world. We've demonstrated as a space community that we can collaborate. So the International Space Station is a huge and a wonderful example of how we can do really hard things together as a global community. And we hope to extend the ISS arrangement to the Gateway and have partners. And again, ISS has permanent partners, and there's only few of them, but we have 10 times as many countries collaborating on the Gateway, on the International Space Station as a permanent partner. And we hope that that would be the case on the Gateway as well. And that we would work with, traditional spacefaring countries like Japan, ESA, Canada, and others, but also countries with whom we have not had as many collaborations in the past, especially in human spaceflight, like India. And I am personally really, really excited for human collaborations with ISRO and the Indian space community.
Thank you. AJ.
Yes, sir.
Thorium has been discussed on the space show since almost our opening program 20 years ago. And it was discussed before that. It's not a deep, dark held secret. What makes it special today in 2022 that we're actually going to see thorium put into power plants. We definitely need the power. We need it here on Earth. We're going to need it in space. Bill Gates is supposed to be building a small demo thorium plant, I think in maybe it's Wyoming or Montana. I'm not sure which of the
Wyoming,
state.
yeah.
Wyoming. Why today? Why not 10 years ago, 5 years ago? We know where the thorium is. Why not? What's held us back?
Well, I guess one of the things that has changed is the situation. We did not have the emergency of climate change in 2000. We did not have emergency of energy requirement to the extent that we have now. So both of those things together are asking for a different solution. In the 70s and 60s and 70s, we had different needs actually. The needs were to have bombs, plutonium, and plutonium was what was needed at that time. And so we had to do things with uranium at that time. And so we sort of, this program was being done at ORNL, but it was canceled by Nixon. Now, of course, the needs are different. And because of that, and the idea of the molten salt thorium reactor, which is a little bit new. Even India is not doing molten salt thorium reactor. They are doing solid. And so all those things are kind of new in the sense that they have not been, really looked into, and actually it is a little bit difficult right now with the regulations from NRC and other places for that to be done even at university level, which it should be, I think, now. So I think the things are changing, and I think a lot of people have started paying attention to this now in last, even last year, couple of years, and so I think that we need to ride that, bull, basically, so to speak, and go forward and do some of this research R&D that is required to see if the molten salt at 700 degrees centigrade or 1200, as I'm suggesting with CSIC, can actually be good to have for a certain duration of time. So those kinds of things need to be looked at, and they are not, and they should be.
Thank you. I believe we have time where I can take some questions from the Q&A channel. So I'm going to take one from Paul, and let's see, Bhavya, this is for you. How do you foresee resolution of the political challenges with the other countries such as Russia and China trying to colonize the moon and starting wars in space?
So I think space is how we actually end wars. Space is in 1967, when the Outer Space Treaty was signed, it was about peaceful exploration of space, and pretty much the entire spacefaring world and beyond has signed the Outer Space Treaty. So I think space is seen as a place where we kind of go beyond and be beyond our sort of differences terrestrially. Despite all of our differences on Earth with Russia, for example, our ISS collaboration has gone very well for over 20 years. So I'm actually, and again, I am NASA. I wear a white hat. We don't talk about war. I actually believe that places like NASA, ISRO, and the broader space community is what is going to help us kind of look beyond our differences. And again, taking off my NASA hat and putting on a sort of a broader citizen hat. I think these are things we need to, there need to be discussions, dialogue is how we will get to going past some of these, challenges on Earth. The Russian ASAT test a few weeks ago was terrible. It could have harmed the space station. It could have harmed Russian and American astronauts on the station. So we need to have dialogue to stop things like that. ASATs are we all are talking about settling space. By the way, if I could make a request to everybody who's on the on the panel, and especially this is, a community of Indian American engineers and scientists. Let's stop using the word colonize when we talk about space. I mean, let's talk about settling space, exploring space. Please do not say manned space flight. It's crewed space flight. So just a request. So yeah, I think it's exciting that so many different countries would like to be part of this, to continue space exploration. I think we should be, collaborating to the extent feasible with Russia, with China, with the rest of the world. Space is hard, it's expensive. We are not going to get anywhere without working together.
Thank you. I have another one, and not sure who it's addressed to. It's from Ravi. It says, Professor, we have learned many of the medical and pharma-related solutions from ISS. What would be the incremental advances needed for us to carry space medicine from ISS to a settlement? You want to take, you're the one listed as professor.
Yeah. Well, I'm not a medical doctor, but I have read some of what they've said, and we know that from the space station, even a short duration can cause decay of demineralization of the bone. It can cause vision problems, a whole host of problems. And I'm sure a lot has been learned at the space station. But again, that's microgravity, and we're not sure what will happen in 1/6 gravity, whether the variations are linear with gravity, nonlinear with gravity. So I think it's very hard to predict. And certain things we will only learn really when we have people on the moon for some extended stays, especially things as far as physiology. I think the low gravity effects are one of the most difficult challenges for us to do on Earth and figure out how that will translate to the moon. And the medical aspects are certainly a big part of that.
I think.
And if I could jump in also, David, I think the other part is the radiation environment. I mean, the radiation environment in low Earth orbit is very different from deep space. And again, we need to continue to learn how, all of the things that we're just talking about will respond to the galactic cosmic radiation environment.
Well, and
solar radiation.
I would just jump in and say, maybe we have a lot of pharma and medical solutions that may or may not work or help mitigate problems, but I've heard nothing about pharma or medical that's going to mitigate the toxicity of lunar regolith, both to equipment and robots as well as to humans. And if you want to know when we're going to space, everybody, with humans and going to go to the moon, let's follow the development of lunar spacesuits, because we're not going without them. And let's follow the development of how robots can work in 1/6 gravity on Earth. They work in 1G. Imagine a Caterpillar tractor or a John Deere or something working without gravity. How would it do that? How would it dig? How would it bulldoze? So how are we going to have robots do this in 1/6 gravity? And how are we going to protect them against regolith? So watch the technology development of these items to get an idea of a really honest timeline for when humans can go and start building and developing, and robots can start preparing the way for humans. And along with this, Ravi asked, we have no alarms from Apollo or ISS that tell us we cannot manage shielding from radiation. So I think he's saying we ought to be able to handle radiation. Okay, who wants to tackle that one? Anyone?
I would say we have learned a lot about radiation, but I think as Dr. Lai mentioned, being on the moon is different than being in low Earth orbit. In low Earth orbit, you have a lot of shielding from the atmosphere and the Earth, and on the moon, you're exposed to half the sky of radiation effects. We're talking about radiation effects on electronics, on machinery, on materials, and of course on humans. And so, anytime we talk about expanding our settlements on the moon and making them more than just something we bring there and live in, like a pressure vessel, Then we're talking about construction and logistics and a lot of operations where both machines and people are going to be exposed to that radiation for long durations. And that's a real challenge. And there are a lot of issues to still resolve on that front.
If I may just interject just a little bit here, we are not really talking about 1,000 people living there, for a year or two or more or something like that. I'm really talking about a few hundred people going back and forth from Earth to the moon to do this work that needs to be done there, including building and mining and all that, and then coming back. That gives a more reason and more impetus, incentive for the commercial companies to also get involved. So all of that together will probably make for a good case or even a business case. And so I'm not talking about 1,000 people living there. That's what I mean.
It is incremental and with a lot of on-the-job training, and
Yes.
The more incremental and the faster we can do it safely, the more we learn and the better we can do it.
Right, and more people going there and coming back and all that will excite the Earth more also, Earth people more also. So I think yes, sorry.
Okay, sorry, I didn't want to step on you. So are you finished?
Yes, I am. Yeah.
Okay, so one last question is from Murtaza, and I hope I pronounced your name right. If not, I apologize. Dr. Lal, and I think this is referring to the Artemis base camp. Is this going to be uranium-based, and what solutions are being looked at for reducing the size of the reactors compared to those on Earth?
So I think you're talking about the surface reactor we want to have on the moon. Yes, it will be uranium based. We hope low enriched uranium. And one way, I think one reason reactors on Earth are large is because they produce thousands of megawatts. For the initial reactors on the surface of the moon, we're talking about tens of kilowatts. So sort of by definition, it's less uranium, less shielding, less everything. So we hope that these reactors would only weigh, thousands of kilograms and not, and I'm not sure how much terrestrial reactors weigh. So short answer, this is a small reactor. We are starting small and then we will go from there. And if we need more power, we just have multiple reactors, modular sort of, basically hooking them in series to maybe get, hundreds of kilowatts. And initially, as we get started, even if we are doing ISRE on the moon, and I hope we are not going to need, megawatts of power. Initially, it'll be small, tens, hundreds of kilowatts, and we will grow incrementally. I think sometimes, and again, NASA has this tendency, as the rest of the space world, since we're all scientists and engineers, we like to go to the big stuff. I think it may be better to kind of go, what's called crawl, walk, run approach. So let's start small and then go from there.
I want to say a couple of things. People look at NASA kilopower experiments, and I think Lockheed has been doing kilopower experiments, and they're getting lots and lots more power with much, much smaller reactors and devices. So it's really interesting to follow this. The other thing I might add is that the commercial fusion industry is really different than the government-led fusion efforts. And there are roughly 35 fusion companies working to come up with some kind of fusion with alternative fuels around the world, and they're raising money. So 2 companies raised close to $1 billion in 2021. One of them is associated with MIT, and I don't remember the name of the other one. But keep your eye on what fusion does, the fact that it uses alternative fuels, and the fact that it's much safer and smaller. So we may see that in our lifetimes, or at least the lifetimes of some of us who are younger. I should say some of you who are younger. I think this is our hour. So I want to thank each one of you for your participation and your commentary and your work and your time. And I want to thank the participants for their questions and answers and attention as well. And it's a great conference so far. Thank you for including me.
Thank you very much.
Thank you.
Thank you, Dr. Livingston, for moderating this panel. You know, I've been in this aerospace profession for now almost 40 years, and with school and